My name is Claudia Reyes. I'm a PhD student at UNSW. And today I'll be speaking about our work with the Open Cluster M67, our modeled isochron, and the seismology of the clusters, subgiants and red giants. So M67 is a well-known open cluster. It's good. It's known as a good testing ground to learn about stellar evolution. And this is thanks to its near solar age and metallicity, its very low reddening, and a rich stellar population. So these are the reasons why it has been targeted for seismology studies of solar-like stars with ground-based telescopes, and more recently with one campaign of K2 data. One campaign of K2 data is about 80 days. Okay, so as I was saying, K2 is the follow-up mission to the Kepler campaign. And one campaign of data is about 80 days of observation. So after the initial campaign of data, the K2 mission visited M67 again for 2 more campaigns. And today I'm presenting part of my results using all 3 campaigns of data. So I mentioned that I use seismology in my work. And what is seismology? So surface convection in stars cause starquakes. And these starquakes travel through the star as acoustic waves and cause the surface of the star to oscillate. And the frequency spectrum of the star reveals the oscillation frequencies as sharp peaks. And we can obtain this power spectrum from applying a Fourier transform to the time series or light curve. And the longer the light curve, the better defined will be the peaks in the power spectrum. And the important thing is that the frequency of the oscillations in this power spectrum would be characteristic of the stars that we are observing. So this thing that I'm showing here is the power spectrum of the sun. And you can see that the peaks are shaped as a Gaussian, and the frequency at which the sun oscillates with its maximum power is known as nu max. So in the sun, nu max is about 3,000 microhertz. The scaling relation that I'm showing down here is valid for all stars with solar-like oscillation. Equivalently, we can use this equivalent equation to obtain the surface gravity of a star. So going back to M67, we were able to detect excess power characteristic of solar-like oscillations in giant stars and subgiant stars. And applying this scaling relation for surface gravity and comparing to our model isochron, you can see that all of the stars fall nicely on top of the isochron. In total, we detected we made seismic detections in 50 stars from a nu max of around 1 microhertz, which is the star at the top, to a nu max of around 800 microhertz. So the isochron fitting is an important part of this work. We made this isochron with models made to fit as best as we could. Especially for this project, we used Gaia photometry, correcting the parallaxes star by star. We also use star by star extinction correction. I don't know if I mentioned that we use MESA models, and we made sure to avoid all these traditionally used simplifications that are not good simplifications for giants necessarily. So for example, the mixing length that we use is often a fixed value model after the sun, but we don't use that. We take a value of mixing length from these hydrodynamical 3D models of stellar atmospheres, and at each step of the model evolution, we look at the log G and we look at the effective temperature, and we take that value from that grid. Now, unfortunately, that grid stops at a log G value of about 2.4. So that's where that segmented line is. So above that line, we really don't expect the isochron to be necessarily such a good fit as it is below that line. But you can see we already have a pretty good fit. So the other thing that we took a lot of care into was with the core overshooting. So the core overshooting is also normally used as a fixed value, but we chose to use the expression by Vanderveer, which gradually makes the core overshooting extent increase with mass. And we calibrated that expression to our cluster M67, which is shown as color in that highlighted panel. Now, when we compare our calibrated overshooting values with independent studies from eclipsing binaries, for example, you can see that it follows pretty well the outer line of their independent results with other models and with other stars. So we are pretty confident on that as well. Now, in summary, we achieved a good fit from the main sequence to the giants, and especially around the terminal edge main sequence is a very good fit with the cluster. So now that we have the model isochron, we were able to test our models with the astroseismic data from the stars. But what is that astroseismic data that we took? So there are two important frequencies, nu max, which I already mentioned, the maximum oscillation power. And the second important frequency is delta nu. So to explain a bit what delta nu is, we have this power spectrum of a normal giant star, and the numbers on top of each frequency peak denote the degree of the mode. So as you can see, there's a pattern here, 0, 1, 2, and then we begin again, 0, 1, 2. So that distance before the pattern begins again is called the large frequency separation, which in this star is 8.2 microhertz. So once we have those two frequencies, we can construct what is called an Eshel diagram, where the spectrum is cut in segments of width 1 delta nu, and then we stack up those segments, and if we calculate well delta nu, the modes will align. So this animation will show this, so we're stacking up the segments, and we see the alignment of the modes, vertical alignment. So that is what we look for when we compare the models with our observations. So for example, these are 4 stars representative of different evolutionary states in the cluster, and you can see that there are 3 red giants. We know they're going to have good signal to noise, but we even had really good signal to noise still for subgiants, which are known to have higher noise levels. So how do we get the oscillation models? We take models from along the isochron, we run them through this other code, which is called gyre, and this will give us oscillation values. But we know we have a problem. The models of the surface are imperfect, so they will not align perfectly with the observations. So what we do, the pink one is the model, and we correct for this using the parameterizations by Boyle-Lisson, and this results in this nice orange model here. So we define the effect that was applied, or the correction that was applied to our stars, by measuring that the value of that correction at nu max. So for each star in our sample, we have a value of nu max and a value of that correction. Because this is caused by imperfect modeling of stellar atmospheres, and we know that atmospheres vary smoothly along the isochron, we expect that the surface offset will also vary smoothly along the isochron. And plotting the individual values from the stars, we see that this happens. So recovering the smoothness of this sample, we use a power law, and for comparison, we show the value for the sun And we see that it goes right through the sun, which is a good confirmation that this is a good example for us. So now we have this expression which then we can use to correct a large grid of models for this project. Another thing we can do with these scaling relations is to express them as mass and radius. So if we combine these two expressions, we can get all of these expressions for mass. And it has been found that the third one in particular reduces mass dispersion and the uncertainty in the global cluster form. So we already have a good estimation of the mass with seismology, but this expression would give us a even less scattered expression. So we have the effective temperatures and the luminosities we calculate from the volumetric magnitude, which we take from Gaia magnitudes and volumetric correction tables. So the interesting thing is that we have reached very similar values of masses for the stars in the cluster using these scaling relations from the oscillations of the stars, these two frequencies that I showed you before, and with the isochrone that we took a lot of care to make as precise as possible. So this is a good result. It confirms that we have made good models for these stars, and we can do this with seismology, which was a pretty good result, but we can also do other things. So one of the things that I'm working on is to use the expression that we derived for surface correction in a model in a large grid to fit individual frequencies and do a more detailed seismology analysis. That will be in that paper that is in preparation.
Very interesting results. I have a question for the Annenberg et al. Parameterization of overshoot. And so you conducted to observational data from the Paris and the red sample. So, but in the open cluster M67, you probably will have had also more massive stars, right? So, do you know how well the Annenberg parameterization, so how well it compares to larger masses of stars? So, have you done this comparison?
No, so in the cluster, we don't have more massive stars than 1.5. We have only less massive than 1.5 in this particular cluster.
And so for the comparison, we did a grid study running MESA models which differ in mass and in the exponential overshoot parameter for the isochrone footing, right?
Overshoot. Yes, exponential overshoot. Yeah, so yes, we use overshooting. The expression there is from Vandenberg. He first published it with another study with M67, but he didn't use exponential overshooting in that study. So we had to calibrate everything again.
Okay.
Thanks, very nice detailed work. Using mass loss in your models?
Yeah, so I did use a very modest amount of mass loss, so a Reimers parameter of 0.1. However, we don't see indications of mass loss, but that doesn't mean that we think there is none. We just don't have enough data to say if there is or not.